Alright, so in this video, I would like to make some comments about Ohm's law and the equation for resistance that we discussed in previous video. So the current that flows inside of a wire, it's there because of the existence of an electric field inside of the wire. That electric field is there because of there is a difference in potential across the wire that we call V. The length of the wire, we call it L. The cross-section of the wire is A, and the resistivity of the material is rho. So one of the equations discussed was that the resistance is the resistivity times L divided by A. A second equation that we discussed in the previous video was V equals I times R, which was called Ohm's law. Let me start with that equation first. I want to make a few additions to this equation to have fully help you understand and be more careful about how you use this equation in a circuit. So the first thing that I would like to add to the equation is the symbol delta V. I would also like to add a minus sign in front of IR. So let me explain to you why. The first point about delta V is based on the fact that the electric potential is a property, is a value, volts. It's a value that all points in space have. So it refers to the potential. V sub A refers to the potential at a specific point in the conductor. So let's say on the left hand side we call that side A, so VA is the potential there. Another value of potential that might interest us is the potential at point B on the other side of the wire. So this point has a potential V sub B. Now these two values, V sub A and V sub B, are not equal to V, what was written in the equation for Ohm's law. In fact, that V in Ohm's law is neither V sub A nor V sub B. What it should be is delta V, which is the difference between V sub B and V sub A. V sub A and V sub B are different if the two points in that wire were at the same potential. We wouldn't have an electric field, and therefore we would not have a current. There has to be a difference in potential across the wire. Therefore V sub A must be different from V sub B, and the important number that goes into Ohm's law is the difference between those two potentials. I'm going to define that delta V as always referring to the potential at a point downstream minus the potential at a point upstream, where the downstream direction refers to the direction of the flow of current through the wire, through the resistor. So that explains why the symbol delta is important there. Also, notice the minus sign. Why is there a minus sign there? So a lot of times when we write Ohm's law, we don't write this minus sign, but when we are doing analysis in complicated circuits, it is important to keep in mind that a minus sign is there in that equation for Ohm's law. The minus sign is there for a reason. Let me explain why. So we know that for the current to go from left to right, the electric field must also point from left to right. We know that electric fields flow from high voltage to low voltage. So that means that the electric potential at point A must be bigger than the electric potential at point B. Therefore, whenever we take the voltage at a point downstream and we subtract the voltage at a point upstream, we should get a negative value. So the left hand side of Ohm's law is going to be a negative value, which we have to account for by putting a minus sign in front of the current multiplied by the resistance. So in reality, this minus sign is there to remind us of something. Is there to remind us that if we move across a resistor in the direction of the current, then the voltage should drop. As we move in the direction, downstream direction, across a resistor, across a wire, we're going to end up at a point that has a potential lower than the point where we started. A useful analogy for this is the analogy of the flow of a river and electric current. So a river, as you all know, flows from high ground towards low ground. In this analogy, the height of the terrain is given by the electric potential, and the river flow is the same in our analogy as the current in the circuit, in the resistor. So that current, as a river, flows from points with high potential towards points of low potential. So as we move across a resistor in the direction of the current flow, we must be going downhill. We must be going towards lower values of electric potential. The second equation that I want to discuss is the equation for resistance. Resistance of a cylindrical wire is equal to the resistivity multiplied by the length of the wire divided by the area of the wire. It doesn't have to be a cylinder, it could be any shape as long as the cross-section is uniform. So in this equation, we notice that the resistance grows when the length of the wire grows. A longer wire would have a bigger resistance than a shorter wire, everything else being the same. The question is why? So again, consider that the current flowing inside this wire depends on the strength of the electric field established inside of the wire. Now that electric field strength depends on the difference in potential across the wire. Remember that the equation that relates those is the electric field is equal to the difference in potential divided by the length of the wire. So if everything else is the same, you leave the area of the wire the same, the difference in potential delta V is the same, but you just make the wire longer, notice that the electric field, since it depends on the length of the wire in the denominator, with a longer length, the electric field decreases. As L increases, the electric field decreases. If the electric field decreases, we're going to have less current flowing in the wire. So the current goes down, and according to the definition of resistance, if the current goes down, the resistance is going up. It is more difficult for current to flow through a longer wire than to flow through a shorter wire. Another way to visualize this is that remember that resistance is related to the difficulty, to the fact that the electrons have multiple collisions as they go from one side of the wire to another. And if we just make a longer wire, we just add in more collisions to the path of the electron, making it obviously more difficult for the current to flow through this wire. So that's regarding that the dependence of the resistance with L. But also an interesting one, perhaps even more interesting, is the fact that the resistance decreases when we make the area of the wire bigger. So why is that? So let's consider a battery with a difference in potential delta V across the terminals, and let's say that we connect a wire between the two terminals of the battery. This wire has a cross-section A and it has a length L, and it carries a current I, which is given by Ohm's law delta V over R. Now imagine that we connect a second wire, identical to the previous one. We connect that wire again between the terminals of the battery. So the second wire, since it's connected to the same terminals of the battery as the previous one, will have the same amount of current. We said that the two wires were identical. So for the second wire, the current is also delta V over R. So what is the total current that is flowing through the two wires combined? So we have two wires with identical currents I, so the total current is 2I. If we replace the current with delta V over R, we notice that we can write the total current as delta V divided by R over 2. So what we're saying here is that the two wires combined have less resistance than a single wire. In fact, two identical wires connected like this, we're going to call this a parallel connection. Two identical wires connected in parallel have half of the resistance of a single wire. So what does that mean in terms of the area dependence of the resistance? What this means is that if we connect two wires, each one with a cross-section A, the result is going to be a resistance of the combined wires being R divided by 2. Clearly, two wires, each one with a cross-section A, are equivalent to a bigger wire, a single bigger wire that has an area 2A. So a thicker wire with twice the area of one wire would have a resistance that is half of the resistance of the thin wire. So what we see here then is that everything else being the same, a wire twice as thick carries twice the current, and its resistance is therefore half the resistance of the thin one. So that is related to this equation. As we make the area bigger, the resistance of the wire should decrease. Perhaps a useful analogy to understand this is the following. Think of a wire as a highway. So a highway has multiple lanes, and we know that the more lanes that we have in this highway, the easier the traffic flow is going to be. So the analogy here is between the wire and the highway. The thickness of the wire is related to the number of lanes in the highway. A thicker wire has more paths, more lanes for the electrons to take to go from one side to the other. Therefore, a thicker wire has less resistance. It is easier for the current to flow through a thicker wire. Alright, that's all I have about this topic. See you in the next video.